Hi everyone, I'm Jan Sharma. I'm a master's student in AI and BME at Carnegie Mellon University, and this work is done by me at the Computational Neuroscience Lab at IIT Madras during my undergraduate degree. As we all know, Parkinson's disease is a neurodegenerative disease which affects mostly old citizens, and it is caused by the depletion of the dopamine in basal ganglia of the brain. So our point of interest for today is these two particular neurons called the ST and GPE loop, which as theories show is the engine of exploration for the brain, in which because it causes rich chaotic dynamics in terms of firing pattern in for normal people, while for Parkinson's it shows a synchronization in firing patterns. So therefore, the theory underlines that the basal ganglia is involved in error-based learning for the brain, just like reinforcement learning, in which exploration and exploitation of actions is done to present action selection methods for the brain. So therefore, the schematic of the basal ganglia, the ST and GPE loop is responsible for presenting rich chaotic dynamics for the brain. And this particular arm of the basal ganglia is termed as the indirect pathway, which fronts the exploration characteristics of the basal ganglia, while this particular arm of the brain is called the direct pathway, which is responsible for exploitation of the basal ganglia. Exploitation can be seen as utilizing or taking up the same action and again and again, while exploration can be seen as a scan of the entire event so that we can decrease our cost function to the minimum value. So in order to simulate these rich chaotic dynamics of the ST and GPE pair, we use chaos theory, in which attractors such as the Lorentz attractor are substituted in place of the ST and GPE loop. Therefore, we use the Rossler attractor in this case, which is defined by these three ordinary differential equations, and we highlight the constant A, which by the bifurcation diagram we can see that smaller values of A shows periodic behavior, while higher values of A shows chaotic behavior. And in the final diagram of the model that we produce, it is quite similar to the basal ganglia with an input going to the cortex, which is split to an arm of the indirect pathway. And as you can see, a network of Rossler attractor has been substituted in place of the ST and GPE loop. While so this particular arm it causes the exploration in the basal ganglia, while the D1 to GPI arm resonates for the direct pathway, and this particular arm is responsible for exploitation. And the choice between exploration and exploitation is defined by epsilon, which is the exploratory parameter, where epsilon equal to 1 goes to exploration, sorry, and for epsilon equal to 0 goes for exploitation. We initialize epsilon as 1 because in a new environment, it is always advantageous to start with exploration of the environment. And here we can see that delta is termed as the error, in which is the difference between the expected reward and the actual reward. And to mimic Parkinsonian conditions, we clamp the values of delta. So and moving on to the results, a smaller values of A show a perfect periodic Rossler, while higher values of A show a perfect chaotic Rossler. And in the final results, we validate this particular model by the use of an Iowa gambling task, in which is used by psychiatrists to test the action selection skills of a patient, in which C and D tasks cards are advantageous because they have a much lesser penalty for more or less the same gain, while cards A and B are termed as disadvantageous because they have a high penalty. And as we can see that our model under normal condition chooses cards C and D, and our IGT score increases, while in Parkinsonian conditions the IGT scores remains more or less the same because of the hindered feedback. So in conclusion, this model presents itself as a proof of concept of the reinforcement learning, error-based learning of the basal ganglia, and the replacement of the Rossler attractor in terms of the ST and GPE. Thank you.